So lab 4 is about simulation and computation. We've been looking at pretty basic functions of Minitab so far. We really haven't looked at simulation in any meaningful way. So this is the first lab that introduces simulation, and we'll be looking at two discrete distributions to motivate that example of simulation. And we'll also be looking at how to use Minitab to compute probabilities for known discrete distributions, in particular the binomial distribution. So this has both components to it. I want you to turn to page 46, which are the questions for this lab, and we'll use those questions to motivate the lab. So please turn to page 46 and just open up Minitab. Okay, so for question 1, I'm going to come back to that later and talk about what I want you to do for that. I'll simplify it in a very basic way, in a key way. But let's start with question 2. Question 2 is about the following experiment. So let me just define what that term experiment means. In this question is used in a particular way, in a very precise way. Let's just define it. So the experiment is defined as such. Toss a fair coin 10 times and record heads. The number of times you get a head. So when you toss a coin, you can get a head or a tail. And the experiment is to toss a fair coin 10 times and record the number of heads. So the probability of a head is, in this case, 0.5 on each toss. Okay, 50%. Okay, so that's how they define the experiment in this question. Let's look at part A. It says use Bernoulli experiment. Actually, say use a Bernoulli simulation to simulate 6 repetitions of this experiment. So they want you to repeat this experiment 6 times. This particular experiment. And they want you to do it via a Bernoulli simulation. So let's see how to simulate. So to simulate, you always use calc, random data. Okay, that's all what you use for simulation. Calc, random data. And then you choose the Bernoulli simulation. Okay. And here we will simulate one experiment at a time. Okay, so I'll probably simulate three such experiments, and then I'll leave 3 for you to do or whatever. I mean, it's the same process in every experiment. So the number of rows of data to generate is the number of times you flip the coin. That's 10. And we store the result in column C1. The output is in column C1. And the event probability is 0.5 because it's a fair coin. Okay? So this is for a Bernoulli simulation. Because we flip a coin 10 times. And when
for question number 1?
This is 2A. And then you get a list of zeros and ones. So the ones over here represent heads. So the computer randomly now simulated this. So the computer got a head the first time, and then it got a 0, and then a tail, and then another head, try number 6, and so on. And of course, you'll get different values from me, because this is all random. So the list that you get will be different from mine, for obvious reasons, right? That's why it's a simulation. So this list of 10 zeros and ones represents a simulation of the experiment. So that's one experiment, okay? This is one experiment, as defined by that over there. Yeah. Yeah, which part are you unclear about? Okay, how to simulate. All right, so simulation is always the same. Use calc, random data to simulate, okay?
Professor? Like when
Just one second, let me just finish, then I'll take a question. Yeah, just quickly, why don't you have a seat? So use calc random data and then you select the distribution. In this case, the Bernoulli distribution. And the number of rows in this case is 10. You store the result in C1. And the event probability is 0.5. Okay?
Why is it 0.5?
Because it's a fair coin. P is 0.5 because it's a fair coin. If it was an unfair coin, P would be different, right?
So fair always means 0.5?
Yeah, it could mean 0.5, but if you have like a six-sided thing, then a fair thing would be 1 over 6, right? So if you have a dice, and it's a fair dice, then it would be 1 over 6, the probability. So fair means that it's...
Oh, 1 over 2, because you have 2 choices.
Yeah, if you have, like, in this case, there are 2 choices, so it's 1 over. So, yeah, that's a good question, right? So that's pretty clear. Okay, and that's how you simulate. You had a question or something?
Yeah. Do we need to repeat this 6 times?
Yeah, I'll just do another one. Let me repeat this for C2. So you do calc, random data, Bernoulli, and you store it in column C2 now. And then you do it for 6 times, right? You do it C1, C2, C3, C4, C5, C6. So each column is an experiment in this case.
And then in sense that you have to display it on the window.
Yeah, you can just copy and paste that for your answer, the result of that. Even if it's not adjusted properly, it's fine. That's okay.
So we keep the numbers the same, we just change the C1, C2, C3, or?
Yeah, you just change the output column.
But the 10 and the 0.5 they stay the same?
Yeah. I mean, you know, if you want to understand simulating a Bernoulli variable, you need to know a bit about the Bernoulli distribution, right? I don't want to get into that because that would take some additional time, you know. Did you guys cover the Bernoulli distribution so far? No? Oh, okay. Well, it's just a random variable with 1 of 2 possible values, 0 or 1. It's the simplest sort of distribution. Yeah. Okay, so B, I'm going to leave for you to do, but I'll move on to C, because that's a very important question, C. It says simulate 200 repetitions of this experiment and save the results in the C7. Okay, first of all, if you want to repeat this experiment 200 times, you're going to be stuck here all for 2 hours, right, using the Bernoulli simulator. So the binomial simulator will speed up that process by quite a bit. So you will do all those experiments in one column and at once. So let's just see how to do that. We now want to use the binomial simulator. The binomial distribution is kind of the aggregate distribution of the Bernoulli. So as a random variable, the binomial random variable is the sum of Bernoulli random variables. And in this case, there will be 10 of them. 10 Bernoulli variables, okay? So you go to calc, random data, and binomials, the next one. And in this case, you have to be a bit careful because you want to repeat the experiment 200 times, so you say 200 for the number of simulations. The results you want to store in C7, the results of your simulation, right? The output is going to be a column. The number of trials is 10, because each coin flip, each Bernoulli trial, each coin flip is one of the trials. So you have 10 flips. And the event probability is again the same as 0.5. Basically, these 2 boxes at the bottom are the parameters of the binomial distribution. So all I'm doing over there is specifying the parameters of the binomial distribution. Binomial distribution has 2 parameters. A Bernoulli distribution has only one parameter, right? So a Bernoulli distribution we have specified by 0.5, that was enough. The binomial case, we need 2 parameters. So distributions generally have a different number of parameters. So for example, let me just ask you, since you probably already know this, how many parameters does a normal distribution have? This is the most common distribution in all of statistics, right? So how many parameters does it have?
70.
How many? Excuse me?
I don't know.
Well, 2 parameters. The mean and the standard deviation completely specify the normal distribution. So it has only 2 parameters. Okay, so that sort of stuff you should really know that. I don't know why it's not so well known. Okay, so anyway, we will then click OK once you specify it like that. And as you see now in column C7, each of these boxes is now an experiment. So you do 200 of those, and you get an idea of, how many heads you get and how many tails you get. So let's just that's a simulation of a binomial experiment. That's part 2C. Does anyone have any questions on 2C, this binomial experiment?
So this is basically the final answer of 2C.
Yeah, you just copy and paste that column.
Copy
And,
paste like only the numbers, right?
yeah, you can copy paste the first 31. It's okay. You don't have to copy paste the whole thing. Any questions on that binomial simulation? Yeah.
Why are my numbers different?
Everybody will have different numbers. That's simulation.
What numbers
Okay, so number of times is 3.
Yeah, let me just take that, show you that thing again. The simulation process. This is for a binomial simulation. Cal, random data, binomial. So that's the input I used. Okay, just to remind you of that.
But Professor, when I copy pasted it, it took many pages, like around 4 pages. It's a very long column.
Yeah, you just need to take 30 of those values. Don't need to copy paste the whole
Oh,
thing.
so it doesn't have to be the whole thing.
No, it doesn't have to be, no. Just to give me a sense that you generated a sample that's credible. Okay, and then see, I simulate again and I change, my answer changes. That's fine. Simulation is random. The answer's going to change. Okay, so that's part C. Now D says use dot plot, odd dot plot, because again, it missed something, to describe the data in C7. Does the data show symmetry or skewness? So let's first use a dot plot to describe the data in C7. So C7, just graph that, graph, dot plot, simple, and the graph variable is C7, select that. You know how to do dot plots, right? It's the simplest dot plot, so there's not much confusion here. There's not much to do. The only idea is that you're now taking the simulated results and you're displaying them graphically, right? This is how you do it. So that looks pretty good. Shows us a bunch of things on 5, 4, and 6, and I mean the results you get might not be so symmetrical. So depends on what graph you get. If you get a symmetrical graph, you would say it's symmetrical. If you get a skewed graph, you say it's skewed. That can happen. This is not such a big sample, and people get different answers. Okay? So that's part D. Does anyone have any questions on 2D, the dot plot? All right. Okay, E and F I'm going to leave for you to do. It's similar ideas, nothing new in that. Now I want to move to question 3, which is the computation part of this lab. Okay. So, like I mentioned before, there are 4 parts to this lab course. graphing, computation, simulation, and hypothesis testing. So we've seen the first part a lot, graphing. So now we're seeing simulation, we're seeing some computation. We've seen computation as well before. And then in the end, we're going to touch upon hypothesis testing. So this question 3 is about computation. It's nothing to do with simulation. It's a computational question. A lot of times I see in the exams, students are confused about the difference between computation and simulation. Sometimes the question is a computation question and they start simulating. Sometimes it's a simulation question and they start computing. So you have to keep in your mind as you go through this course the idea of differentiating between those two types of things and be able to do that based on the question given. Yes?
You said there's computational, simulational, and then?
There's computation, there's simulation, there's graphing, and then there's hypothesis testing, which we haven't seen, which we'll see only, I think, when we go to the last 3 or 4 labs. Okay. All right, so question 3 talks about, again, a binomial random variable, which is defined by the parameters n equals 10 and p equals 0.1. So they ask you to find a certain number of probabilities. Okay, the thing about this is that, first of all, you have to be clear in your mind what this binomial random variable looks like, okay? This is very important. So the parameters in this case are n equals 10 and p equals 0.1. So the possible values of x, the binomial random variable, are what? What are the possible values of x? X could be 0, or 1, or 2, or 3, and so on, till 10 actually. It actually has 11 possible values. And yeah, that's a bit, when n is 10, you can have 11 possible values. Okay? So you have to use these 11 values as an input column and prep your Minitab worksheet by that, because you will output the probabilities using the program in C11, but the input column you'll first set up with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So just you have to prep C10 with the possible values of the random variable. And the idea is that you're going to expect the output of the Minitab to fall into C11. So the output column will be C11. Again, very important to keep in mind, inputs to Minitab generally come in columns. Outputs to Minitabs also take the form of columns. So this column is the right framework for viewing things in Minitab. All right, so let's compute this probability. How do you compute the values for this distribution? So I'll input this in C10, and then I want to get probability x equals 0 is 1. And I want to get probability x equals 1 is 1. And probability x equals 2. I mean, we could use Minitab to generate these values one at a time, but the better approach is to do it en masse at the start, and then use the table that you've set up to solve your question. Okay? So there is a difference in approach here. Right? There is an assumption in the approach here. Okay, so let's compute this. Calc probability distribution. So you're doing computation, so you don't go to random data, you go to probability distribution, and then you choose binomial. Okay, that's important. Calc probability distribution binomial. And you click this first choice, probability, not the cumulative probability. You switch that from there to there. And the number of trials is the value of n, the first parameter. And the event probability is 0.1. So you're specifying the 2 parameters of the binomial distribution. And the input column is the possible values of the random variable, of the binomial random variable, that's C10, and the optional storage of the output column will be C11. And then when you click OK, you'll get the probabilities right next to it. So the probability that x is 0 is 0.348. Probability that x equals 1 is 0.37. Now in this case, everybody should get the same answer because this is computation, right? Computation, everybody gets the same answer. Not so in simulation.
But I got the same answer, but I got many stars of it in row number 10, and then it started off from there.
Okay, I don't know what specifically that happened, you know, but it should be. Did everybody get this thing? Did you get, you got that?
Yes.
Did anyone not get it like her? Okay, they might be mistaken. Then just do it again. Just do it again. Go to Cal, probability distribution, binomial. Remember choosing binomial, right? And then you should set it up like this, right? Just check it. Just, or maybe you didn't type in this column correctly. Do that also.
When they ask us P x is equal to 6, is that x on what, I mean, sorry, 6 is as what equals in C10? Or as we see on those?
Yeah, I'll get to that. That's a good question. I'll get to that. I'll do A and B for you, right?
Okay, but anyway, like. So
Is that working for you now?
I don't know, I got.
Ours is on cumulative, not probability.
Yeah, it shouldn't be on cumulative. It should be on probability.
Yeah, I did that. I got the same numbers, but I got many stars above them. Like,
Okay, that you'll have to come to me after class about that, okay? Because I think generally people didn't do that, so maybe.
It's fine, but like the answer for number 3A is basically I just copy paste these two columns, right?
No, that's not the answer. That's just the prepping for it.
Oh, okay.
Yeah, that's the initial preparation for it. Then once you have these two columns, then you get the answers, right? Okay. Okay, now let's move to question 3A. It says probability x equals 6. So the probability x equals 6 is just right next to 6. It's 0.000138, right? The probability that x equals 6 is just this in this box. See, that's the output column of the probability. So the probability that x equals 5 is, for example, this one. The probability that x equals 1 is 0.387, for example. The probability that x equals 2 is 0.19, and so on. So that should be pretty clear. Any questions about that? You see that what probability of x is? X equals 6 is? It should be pretty straightforward, right? That's why we did. That's why we generate that column, to generate the probabilities of the random variable. Okay. B says probability that x is at least 8. This is a bit. So B says probability that x is at least 8. So x could be what? 8, 9, and 10. 8, 9, and 10. So x equals 8 plus probability, x equals 9 plus probability, x equals 10, right? So you add them up, and you get, what do you get? 0, because the probability of x equals 8 is 0 and x equals 9 is 0. I mean, it's interesting, but this simulation can be thought to represent 10 tosses of an unfair coin such that the probability of a head is 10%. Right? So when the probability of a head is 10% on an unfair coin, then the probability that you get 10 heads or 8 heads is almost non-existent. It's 0 almost, right? And that's why the probability that x equals 8 is coming to 0. That's fine. I don't mind that. I'm not going to be picky about it. If you say 0, you say 0.0000, you know, something. It's fine. It's not a trick question. But I think it's important to keep in mind, I didn't mention this at the start, but it's important to keep in mind what this binomial distribution represents, right? Or can be visualized as. That's one way of looking at it. An unfair coin tossed 10 times, because n is 10, and the probability of a head is 10%. So then this sequence of numbers makes sense, the values of x. So the rest are pretty straightforward, just the same way. I'll leave C and D for you. I'll do A and B. But any questions about 2B? Is that clear? Okay. That's question 3. Question 1, I want you to have a look at by yourself, but I'll change one very key thing in it. Question 1 says, consider the following probability experiment. Please just follow the question with me. It's very important. It's very important because it'll save you trouble later on. And I'm simplifying the question markedly. In fact, I'm making it so that it's just like example 1 on page 39. I'll explain that. Consider the following probability experiment. Roll a fair dice 2 times and record the sum. Don't do that. Just do roll a fair dice once and record the result. Call that result x. Okay? So consider the following probability experiment. Roll a fair dice once and call the result x.
And call the result x.
Yeah, that's the question. The hint for question 1 is that it's exactly like, almost exactly. I mean, in example 1, they simulated 200 times, here you simulated 500 times. It's exactly like example 1 on page 39. So I want you to have a read of that example. That's the only thing I want you to read in the lab. Everything else is covered by the material we did. But I want you to have a look at that example only for the reading and use that to do question 1 because it's a carbon copy of that. There's nothing else you need to read in the lab. Okay, that's the lab.